Good morning and welcome to today's Military and Aerospace Electronics webinar. Take flight with assurance, the importance of hardware-in-the-loop verification. Sponsored by United Electronic Industries, AMETEK. I am Jamie Whitney, Senior Editor of Military and Aerospace Electronics at Endeavor Business Media, and I'll be hosting today's presentation. Next, I'd like to introduce our speaker. Mr. Erik Goethert has designed, managed, and implemented applications that collect real-world data for aerospace and industries so engineers can build smart systems that are reliable, flexible, and rugged. He has more than 25 years of experience in industry-wide hardware, software, and I/O application solutions. He has an engineering degree from Cornell University. Erik, please take it away.
Thanks, Jamie. And yes, today is Take Flight with Assurance, the importance of hardware-in-the-loop verification. So let's see, is your product ready for prime time, or is it stuck holding up traffic? Are all your systems go? Have you verified functionality so you are ready for takeoff? Don't let any hidden or unvalidated systems put your product at risk. Let's dive right into design validation and verification. So yes, I am Erik Goethert. I am with UEI, and today we will review how to accelerate your time to market. Yes, by using a mix of virtual models and real components, you can verify earlier and more often. We will discuss verification and validation in context of the V model. I guess that's somewhat redundant, but what we do is we hope to show you how to avoid redundant tasks and reuse all that code and models throughout your journey. Here's a quick agenda. First, let's discuss the V model and how that can help frame the conversation. Then, applying the need for earlier validation and verification, we can build a system. And then create a checklist so we can ensure we reuse components along the way. Well, this is verification and validation. They are independent procedures that are used together for checking that a product, service, or system meets requirements and specifications that it fulfills and that it fulfills its intended purpose. This definition is from Wikipedia, so it must be correct. Verification is typically testing so that the device or system is shown to meet the design specs, while validation is more user-oriented, testing that the device or system meets the requirements of the user's needs. Some of the various methods to verify and validate include HILs, SILs, and hybrid test benches. So let's set the stage here. Hopefully, everyone out there is familiar with the V development model. Whether you are in software development, hardware development, or systems, this model is entirely applicable to show how each phase can influence the next, from conceptual models all the way to deployment. Typically in our world, the closer to the left-hand side of the V, there is more simulation to prove out concepts, while on the right-hand side is real hardware to be validated against these requirements and the models. And of course, I can't forget moving towards certification. So we can pull out the various simulation and testing needs along the way, starting with 100% simulation. Typically, the system or unit is simulated using a CAD tool to prove out the concept. That's typically on the top left side. As we get into more detailed design, more unit testing and component testing is needed. However, some of the supporting signals or systems will still need to be simulated. They may be still under development or just easier to model with a simulation. Many times, this is on a single test bench. Moving back up the right side of the V, after a component is identified as a good candidate, hardware-in-the-loop testing is done for integration testing. More of the other components are real, while some are still simulated. This is done perhaps in a system integration lab or on a hybrid test bench. If a candidate passes the verification criteria, sometimes it will be integrated in a full fidelity simulator so a pilot can fly it, basically. Better to test on the ground. Eventually, testing is completed on the vehicle in real-world conditions with instrumentation. There is ample opportunity here in this design pattern to reuse models, code, and of course, the hardware. Is this opportunity lost at your company? Let's look at some of these challenges. So I guess first we need to define a couple terms. On top of the list here is hardware in the loop. We can safely state that an embedded system is best tested with real hardware under real conditions. However, most times this is very expensive, both in time and in cost. So the next best solution is to simulate the hardware with a model and use that to exercise the system or to test with a mix of real and simulated hardware. This can help with the test coverage since the parameters can be easily changed in a model to a value that should be never seen with real sensors and hardware. Next up is System Integration Lab, and it has all the components in a system to be exercised and tested. Any that are not present can be simulated, as well as most of the signals from sensors. I have heard the term cockpit on the ground. Many times, this can include an actual fuselage so a pilot can fly the system while it is on the ground. A hybrid test bench I have seen from our European customers. This is a mix of real and simulated components. Seems to me we should all agree on common terms because from my 20,000-foot view, they all mean roughly the same thing, or at least they have very similar system characteristics. Just look at this simple system. There are all the controllers, sensors, as well as miles of cable harnesses. Why go through all this effort? Why cable up all the controllers, the sensors, the simulated controllers, the simulated sensors? Why bother simulating when you could use the real sensor or the real controller? Well, first of all, it saves money. If the controller is not complete, or if it is expensive, why not simulate it? It is also easier to duplicate a simulated sensor or controller than a real one. Typically, only a few were manufactured initially in the first phase of design and development. It also saves time. Many teams can work in parallel. The functionality can be verified before it is on a physical board. It also increases accuracy. You can simulate failure modes without the actual failure feedback. The flaps can fail to work in a sill. However, they 100% need to work in the air in real life. No need to put the sensor in an oven or a climate chamber. Simulation allows testing outside of normal operating conditions, even contrived or arbitrary ones. Another benefit is the regression test suite. If you have changes, run it against the suite of tests to ensure there are no unintended consequences. Someone once said, trust, but verify. Some of the initial testing that can be accomplished are failure modes. The real question to ask is, can your system pinpoint the failure? Is it real? Is it a sensor, a wire? Is it the hardware itself? Do you test all the extremes, the high, the low, or even the open values? How does your software react? All this is very easily modeled with a simulated system or sensor. Having a method to verify the complete test setup and connections helps you answer the all important question: is that failure real or is it in your design? Demand it from your hardware. Ensure that it's implemented in your software. Through the correct selection of data acquisition and simulation I/O boards, you can easily find hardware that combine functionality to simulate and verify your systems. Analog input, analog output, digital I/O, frequency or counter timer type needs, major avionic protocols, CAN, serial buses, and even customer or GUI inputs and outputs can be simulated and verified. We also have a better way to handle interconnects. Use a computer-controlled interconnect board. The ability to switch in the real signal, perhaps a simulated signal, or even a fault or an open is invaluable for range and error checking. Or switch in multiple different faults. Take control of your HIL, your SIL, or your hybrid test bench. Sure, trust but verify, but don't just verify one point, which brings us to this next point. What is the difference between simulation and test? Well, in my mind, it comes down to one word: continuous. Typical test systems only test one or more discrete points, while a simulation system in a HIL or a SIL is a continuous vector type operation. Any signal or system that is simulated must provide the complete range with reasonable fidelity. Are you testing at one temperature or from -20 to 70 degrees C? Every degree or just 3 points? So let's look at a typical block diagram. The system integration labs, hardware and loop systems, and hybrid test benches all look pretty similar. We have a controller or LRU on the left going through an interconnect panel. The interconnect panel is wired into real or simulated devices, real or simulated sensors, or even other controllers. Depending on what part of the system you are verifying, the sensors could be real, they could be simulated, or the other controllers could be real or simulated. Please remember this diagram for later. So implementing these HILs, SILs, and test benches bring their own challenges. It seems that costs are always increasing and it's taking longer to realize the results. So how do we mitigate these issues? It would be great if we could share the benches and the hardware and start creating these benches much earlier in the development cycle. One thing that the COVID revolution has taught us is that remote testing and shared resources over the Ethernet are not only possible, but they actually do work. Hence this webinar. We can use models or simulations for the components that are not ready to be tested yet. And the hardware can be more accurately reproduce various signals, converting the virtual simulation to actual electronic signals that can be used by the unit under test. Do you have a simulation of your controller, don't you? Or a simulation of the plant? All of this can be leveraged early in the verification process as well as later. Simulations are much more portable and shareable than the physical hardware. We're all chasing the goal of higher availability of the test benches or more comprehensive testing at a lower cost. Well, one solution is standardization. So why not standardize on an approach to solve these issues? The major goal being the reduction of the cost by minimizing development and validation effort of these systems. If the many vendors of the instruments, controllers, and sensors all agree on a model definition, maybe Simulink, then it would give the users a larger choice as well as the ability to combine them virtually to try them out. With more buyers of their systems, the vendors will be incentivized to cost reduce. Also, this will show early on the interoperability between various manufacturers. If we all get together, we can draw out the best ideas from all the different entities. Hopefully, everybody can agree on a common abstraction layer or even a common API. It would enhance the compatibility with the different hardware, software, and operating systems. It even goes as far as reducing the learning curve of the various engineering teams. All the APIs would be identical. Or, in a nutshell, with many vendors of instruments all agreeing on a common driver or hardware abstraction layer, all working together with the final customers and integrators, a better system can be developed. With this in mind, I would like to introduce VISTUS, or the ED247 standard. The ED247 standard is defined by EuroCai, the European organization leader in the development of worldwide recognized industry standards for aviation. The standard is also called VISTUS for Virtual Interoperable Simulation for Test of Avionics Systems. Its objective is to define a common standard so that virtual component models can be shared between the different aeronautic industry actors during the whole product life cycle. For example, for the full simulation of the system, or a hybrid test bench mixing real and virtual components, or even the simulators, the training devices delivered to the aircraft end user. One of the main aspects addressed by the standard is the virtualization of the analog, discrete, and avionic buses. This virtualization is done by digitizing and multiplexing the information on an Ethernet bus, ensuring that the timing of the signals is preserved. That last point is the key one. These lofty goals are shared by these companies who currently have team members around the ED247 working group table. They represent some of the biggest names in aerospace and aero engines around the world, with a good number of key instrumentation and data acquisition system suppliers sprinkled in as well. As we mentioned previously, that the main aspects addressed by this standard are the virtualization of the analog, discrete, and avionic buses. This virtualization is done by digitizing and multiplexing them on an Ethernet bus, ensuring that the timing of the signals is preserved. We need to ensure to minimize the introduced latency by limiting the CPU, memory, and bandwidth usage so we can reproduce the original signal with a high accuracy in magnitude and in timing. So looking at a high-level architecture of Vistas, everything is based on the Ethernet bus with many different components connected to it, from virtual to real to the various tools. So let's review. We have real comet, real components, real avionics, sensors, and the like. They need an I/O bridge or hardware to convert the signals to a Vistas packet and back. This is where the discrete wiring happens. Virtual components generate the Vistas packets directly. These are software simulations of any component and can receive a Vistas packet to modify their behavior. And then the tools components. These include recorders, playback devices, display tools, air injection tools, and such. Each either consumes or generates the Vistas packets. As you see, the backbone is the Vistas packet traveling over an Ethernet network, which can be generated and or consumed by anything. The receiver does not know if it was generated by a real device or a simulated one. It's just a UDP packet. This virtualization makes it 100% usable on both sides of the V development cycle. From full simulation on a single computer or multiple computers simulating many different devices, or even full-on cloud computing. For more concrete or physical device testing, Vistas is great at unit testing where all the inputs in the system are not present and are typically simulated. It is also used in integration testing with more physical and less simulation, and even in the training simulator or flight simulator. In fact, models that generate these Vistas packets can be reused from the beginning to the end of the development chain, and even into maintenance. Here's an example of a test bench that has various devices, A, B, and C. They are interconnected by this Ethernet bus or this Ethernet cable. Any signal routing is accomplished through the software configuration. All the parameters are easily displayed via the display tool. Certainly makes bench design and infrastructure much more simple and generic. And it is easy to substitute a piece of real equipment with a simulation node. After all, it's just UDP packets writing over that Ethernet bus. Another design pattern is the replay or analysis of information gained in flight. The data is acquired and either saved directly into a Vistas format or by a converter node. The data set can then be replayed by the same display node as well as replayed into avionics controllers by the I/O bridge. Whether the data set was modified from the original for air injection, replayed more slowly, or as is, it's entirely up to the user. The device is just consuming Vistas packets and replaying them. This virtual test environment uses IP UDP to connect virtual and real-world hardware to accomplish system tests in an efficient and cost-effective manner. If the hardware is not present, it can be simulated. The simulation can run remotely with the simulation communicating with the hardware via IP or UDP messages. Real hardware can be switched in anytime. The various pieces of equipment can be anywhere. So let's do a quick review. The ED247 standard provides an ultra light way to virtualize the exchanges between real and or virtual components. It includes the capability to log and replay the exchanges between equipment with accurate timing. And it has an I/O hardware abstraction layer, making the software independent of hardware. These capabilities allow for sharing and reuse of the models all along the different development phases. One example is the reuse of the models for the development of the end users' simulators and trainers with minimal amount of work. Models also make for efficient hybrid testing where we can mix real and virtual components, easily swapping between real and virtual components on that bench. This makes the actual realization of distributed testing with the components not necessarily co-located in the same building, site, or even the same continent. Since distributed testing is well supported, this allows for earlier integration testing, even with some components still located at the provider's facilities. The Ethernetization of the information allows for a lot of reduction in wiring and simplification. All this equals a drastic cost reduction of the design and implementation of these test benches. I think I just made up a word, Ethernetization. Here at UEI, we have an I/O bridge configuration mechanism that is very simple and based on two XML files. The first one is based on the ECIC format specified in the ED247 standard. It contains all the information relative to the network aspects, for instance, IP address, port number, and structure of the data packets. The second one is based on a pre-existing XIDML format describing the hardware configuration of the I/O bridge. These include input, output wiring, gain, filter characteristics, and stuff like that. These two files are used as arguments by the Vistus application running on the bridge. The Vistus application can be automatically launched during boot up, making it an instant on type application. So here at UEI, we've been doing tests to evaluate the latency introduced by Vistus's virtualization. Here are two examples. The first one shows the latency of analog and discrete signals, and the second one tests the Erik 429 bus. So let's do a review of the testing of the analog and discrete first. We have a signal generator that sends a step to the acquisition bridge. The acquisition bridge acquires a signal and pushes the associated packet in ED247 format on the Ethernet bus. The replay bridge receives this Vistus package and generates the corresponding signal. Signal produced by the generator and the one generated by the replay bridge are simultaneously displayed on a scope. The delay between both can be easily measured. We're going to do something similar for Erik 429. A moving IMU or inertial sensor sends its attitude to the acquisition bridge through an Erik channel and message. The acquisition bridge acquires and timestamps the signal and pushes the associated packet in ED247 format on the Ethernet bus. The replay bridge receives a Vistus packet and generates the corresponding Erik message. The message produced by the replay bridge is also acquired and timestamped by the acquisition bridge. This way, the latency is calculated through the analysis of the ED247 packets. Well, in both cases, the latency measured was below 2 milliseconds. Pretty good. So why does this work? And how does this help? Since there are no wires, the behavior or system can be virtualized. Once a model is defined at the conceptual phase, it can be reused all the way to the training simulator at the end and anywhere in the middle. It works for local testing of a component or local testing as a hybrid bench for larger systems. Components can be added in as they are available or virtualized when they are not. And the components or even the models do not have to be co-located. Remote distributed testing works. It is currently used across Europe and the United States. Models are being reused for validation testing and even for the flight trainers on the fully vetted and deployed products. How can this help your design process get off the ground and flying? So we found out that distributed verification and validation works. Distributed verification and validation with models and with real equipment works. Here's a checklist to get you started. Determine what the input and outputs are on your device. What are the signals? What need a model behind it for proper behavior? what hardware do you need to simulate or stimulate the devices and signals? One method is to simulate everything, adding real signals as you progress. Find an architecture that is inherently distributed and flexible so you verify early and often. I wish you good luck with your projects.
Thank you very
Thank
much,
you,
Erik.
everyone. Thanks, Jamie.
Perfect. Thanks again, Erik. A few of you have already submitted your questions, so we're going to jump right into those. As a reminder, if you would like to submit a question, type your question into the question window on the side of your screen and hit the submit button. Also, please stay to the end of the presentation to complete the exit survey, which will pop up on your screen. You can preview the questions now by clicking the exit survey icon on the left side rail. All right, let's jump into some questions. Erik, can I use Simulink as the modeling tool and generate the ED247 messages?
Thanks. Absolutely, you can. There are some existing libraries out there. I think some of them are open source that actually generate valid ED247 packets that then can be replayed into a device or used to stimulate or simulate various pieces along the way.
Excellent. Okay, a couple of software related questions. How is embedded software verified and validated?
This is one method to verify and validate embedded software is by looking at your design documents, looking at the edge cases, and running through the expected results from the various inputs and reading the various outputs. That's exactly what this is set up to do.
Okay, and where and how is software tested?
So typically it's unit test in the very beginning before it ever sees any kind of hardware. And eventually, when it's put down on some real controllers on some real hardware, then you get into testing it inside of labs on benches with typically simulated signals going in so you can read the outputs initially, and eventually you get to system level testing.
Excellent. And what are some real use cases for vistas?
Well, we've seen various projects using Vistas, everything from testing your entertainment system that you see when you sit in the seat in front of you, to various components along the way. Various manufacturers, Airbus, Rockwell Collins, have been using um, Vistas-based systems to verify and validate that everything's going to work.
And where can one get the Vistas bridges?
So Vistas bridges are typically provided by IO manufacturers similar to UEI. There's a handful of them out there who have off-the-shelf hardware that supports Vistas. You can go to the Vistas working group, and I'm sure you will see a list of companies similar to ours that also provide Vistas type hardware.
Okay. And do the recording tools only record what is going through the network bus? Is it practical to send additional data for it to log only?
Well, that's up to the recording tool per se. Sometimes we've seen recording tools that record everything in the systems, and then post processing, it gets converted to Vistas packets. And we've seen recording tools that, to your point, take whatever's on those buses and that's all it does. It really depends on what the user is trying to record.
Does UEI have a pub sub, publish, subscribe pattern app to make the communication between the nodes more easy? If not, have you thought about it?
So this Vistas or ED247 is a pub sub type design pattern, and there are setup files that you use to route all the signals as far as who is publishing and who is subscribing. There are certainly other methods to do pub sub type applications. whether it's using a data distribution service or something like Zero MQ, we look at Vistus as something made for the avionic industry.
And one more question for you. How do you do certified flight software?
So we supply hardware tools that assist in the certification of your flight software on that hardware.
Hmm.
But again, it would be up to the user to set up the specific tests, the specific verification patterns to ensure that the flight software is going to do what it's supposed to do at the right time.
Hmm. Okay, avionics systems have deterministic timing and RTOS. Will Ethernet-based structures have problems in terms of deterministic timing?
That's a great question, and typically we have found that at a 2 millisecond or less latency, those systems seem to be fine with it. There are certainly other systems that need tighter timing, in which case you would have a more direct system compared to a Vista system. We are working on different methods of publishing these Vistas packets using something called RDMA, which would make the latency that much tighter down to the microseconds, which would really address some of those RTOS problems and challenges.
Fantastic. Well, I am afraid we have run out of time for those questions we did not have time to answer. We'll be getting back to you via email. And that concludes today's presentation. On behalf of Military and Aerospace Electronics and Endeavor Business Media, I would like to thank Erik for presenting and United Electronic Industries, Amatech, for sponsoring today's webinar, and of course, all of you for joining. Have a great rest of the day.